So this is the answer to the question. I guess that's how this video will start. Here is the answer. Okay, are there any further questions about this before we move on to chapter 11? Okay, cool. Then we are going to move on to chapter 11. Also, if you joined class a little late, we are going to use Top Hat today. I hope we get to the Top Hat questions. I have one at like slide 16, so maybe we'll get there. I hope so.
Can you actually go over that problem before you get into 11?
The one that we just did.
Oh, you just went over it? I was late, so sorry.
Oh, okay. Yeah. Yeah, we went through it. I did not record it though, because I'm an idiot. So if you do have questions about it, the answer was up, and I did save the drawing. So I think I should be able to post it as like a PDF or something.
Okay.
And then if you have questions, just send me an email. But most of those problems or most of the reactions were from chapter 8, except for one that was a radical reaction.
Okay. Thank you.
No problem. Sorry, I forgot to record it. I realized after I had the answer up that I hadn't done it. Okay, so we are picking up on module 11. This is our last chapter. There's a very real possibility that we will have nothing to talk about on Monday, and we will just be able to review before your exam on Tuesday. And then Wednesday will also be a like organic one grand review before you take your final exam on Thursday. So we are doing so incredibly well. I've never been this on schedule in OCHEM 1 ever. So you guys are doing great. So at the beginning of this chapter is about alcohols and ethers and reactions with those compounds. In order to be able to talk about them, we have to be able to name them. We've already done naming of alcohols, but this is a bit of a review. Oh, can everybody make sure that their microphone is muted? Okay, thanks. I think that fixed it. So we need to go back over alcohol nomenclature, which isn't too challenging. I remember the IUPAC format for naming is that you use your alkane prefix and finish it with the OL suffix. So a 1-carbon alcohol, the prefix would be meth. The AN is our infix. It says there's only single bonds. And then OL is our alcohol suffix. So we end up with methanol. The common name is, the format is alkyl alcohol. So you name your alkyl group and then you say alcohol. So methanol, the common name would be methyl alcohol. For a 2-carbon alcohol, we have ethanol as the IUPAC name, ethyl alcohol as the common name. And then next one down, I didn't do 1-propanol, but I drew the structure of 2-propanol because it has a fun common name, which is isopropyl alcohol. And then below that, we have 2-methyl 2-propanol, the IUPAC name for tert-butyl alcohol. So if this is something that you don't remember or that you struggled with initially, please make sure you go back over it. And also remember that I have office hours Monday and Tuesday. Okay, we're gonna do some practice problems. So what I'd like you to do is screenshot all 4 of these. And then I also have some on the next page. So go ahead and screenshot or write these down, and then I'm going to put you into breakout rooms to go over some nomenclature. So I'm gonna give you about 10 more seconds to scribble these out. Okay, and then here's your next set. Since we've already done naming, I believe in you guys. I think you can do this. Okay, when you have all your structures drawn out, go ahead to your breakout rooms. Did we come up with a name for the first one?
We said probe 2 in all.
Yeah.
Would it be? Never mind.
I mean, there are a couple ways that you could order some numbers around. So it looks like you guys had your numbering correct. This is carbon 1, 2, 3. Remember that there is a difference between having your alcohol here and having your alcohol here. So you need to indicate that. So you said prop 2 in all.
Yeah.
Yeah, so you could do prop 2 in, but you'd have to say 1 all to indicate where the alcohol is. You could also do 2 propene 1 all. Yeah, so the alcohol has the priority over the alkene is the important thing there. Okay, what about the next one to the right? This one has a common name that you guys were asked to memorize.
It's benzyl.
Mm-hmm. So this is benzyl alcohol. Okay, bottom left, what's this compound?
That's phenol.
Do you know?
Mm-hmm. Okay, what about the next one? This uses a little bit of aromatic naming, but you can kind of derive it from what you know about naming cyclohexanes.
So the OH would still have priority, right?
Right, so that would be carbon number 1.
And then the methyl would be on 4.
Mm-hmm. So what would you call this?
It'd be 4-methyl cyclohexanol.
Well, so it has the, excuse me, it has the double bonds. So this is phenol.
Oh, okay.
So we just need to use phenol. You'll also learn when you do aromatic chemistry in OChem 2 that there's another way to name this, which would be para or p-methylphenol. So I'm not going to ask you guys to learn that naming right now. I'm just putting that there because that's also technically correct. Okay, cool. Let's go to our next page. These were maybe a little more challenging. In the first one on the top left, where did you start numbering?
From the left, right?
Uh-huh. Okay. Did anybody come up with a name for this?
We didn't get that far.
Okay. What would this molecule be named if this were not here?
Pent 2-all.
Yeah, or 2-pentanol. So you can make it a little easier on yourselves. You don't have to insert the number inside the name. So it could be 2-pentanol or pentane 2-all. And then what is this substituent on carbon number 4?
Cyclohexane.
So it only has 5 hydrogens.
Is it just hexane?
Nope.
Cyclopent.
No. So think about what cyclohexane would look like as a substituent, right? It's attached to something else. It would have 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, 2 hydrogens here.
Hexene?
Not just hexene, not cyclohexene. Because
Double bonds on the inside, right?
right. So we're looking at a substituent that's a benzene ring. And what do you call a benzene ring that's sticking directly off of a structure?
It's a phenol.
Right. So if this was 2-pentanol and we have a phenyl group on carbon number 4, what's the name of this compound?
It's for, would you put 4-phenyl to pentanol?
Yeah. I just watched my very large cat squeeze under the very small gap under our couch. His butt was sticking out for a very long time. I wasn't sure he'd make it. Okay, next compound. Where do we start numbering? What has the higher priority, the alcohol or the alkene?
The alcohol.
Right. So where do we start numbering?
On the left.
Left side.
Mm-hmm. Okay, did anybody come up with the name of this one?
Um, 4-pentene 2-all.
Mm-hmm. So you could do 4 pentene, pentene 2-all, or you could do pent 4-ene 2-all. This is one of those times where inserting numbers inside the name simplifies everything. Because then it becomes very clear that the alkene is on carbon 4, the alcohol is on carbon 2. This works as well. What you can't do is say like 2,4-pentanol. That just wouldn't be specific enough. Okay, next one. What is carbon number 1 on this cyclohexane?
The alcohol.
Right? And then am I going to number in the clockwise direction or counterclockwise?
Clockwise.
Clockwise.
Right. Why do I go clockwise?
You get the lowest numbers.
Right, because that's the fastest route to numbering that methyl group. If we went the other way, it'd be 1, 2, 3, 4, 5 for the methyl and 4 for the alkene. But if we go clockwise, they both get the number 3. So what is the name of this molecule?
Three methyl cyclohex 4-enol.
Well, you want the 3 on the ene as well, right?
Right. 3-methyl, 3-cyclohex enol. You can also do 3-methyl cyclohex 3 enol. Why are we not indicating what number carbon the alcohol is on?
It's just implied.
Right, it's implied because it's a cyclohexanol. That's automatically priority number 1, unless there's something higher priority on the molecule, which there is not. I think so far in this course, we do not have any higher priorities than alcohols. When we
That's
get to
what
opening 2, it gets exciting. Okay, are there any questions on naming? Okay. Cool, we're going to make it a little more fun and start doing the nomenclature of ethers. So there are 2 different ways of naming an ether. There's your common way and your IUPAC way. So the IUPAC is going to be alkoxy alkane. The common is alkyl ether. So I'll show you what I mean by that in a second. So in the first compound, which carbon piece is the longest?
The one on the left.
Right, so this is a 2 carbon piece. So this would be ethane that is substituted with a methoxy substituent. So we could call this methoxy ethane. Sorry, I didn't really mean to put a space in there. Or the common naming would be to list both of the alkyl groups in alphabetical order. So this is an ethyl group, this is a methyl group that just happen to be in alphabetical order. So this could be ethyl, methyl, ether. Okay, so what would be the IUPAC name of the second ether that we have here?
Would it be
Diethyl ether.
Yeah, so the common name would be diethyl ether. What would be the IUPAC name?
would it be ethyl ether?
Just remember, IUPAC is going to follow this up here.
Ethyl oxyethane.
Yeah, so just a little simpler, ethoxy ethane. Okay, the next one over. This one's definitely easier to name in the common way. So you have a tert butyl group, you have a phenyl group. This would be tert butyl phenyl ether. And remember, the tert does not get alphabetized. So this is being alphabetized by BP. We only alphabetize the alkyl prefix. What would, if we did the IUPAC of this, I think that's kind of messy, so we're not gonna worry about that. I would accept the common name for this. Next one down, what is the longest carbon chain here?
5.
5, and are we gonna number from the left or the right?
Left.
From the left.
Okay, and then we have this substituent on carbon number 2. What would that substituent be called?
Ethyl?
Methoxy.
Yeah, methoxy. So this would be 2-methoxy pentane. And usually you wouldn't use common naming for this because it's attached to the second carbon. So I'm not going to worry about that. Okay, the next one. What is the longest carbon chain in this compound?
2.
Mm-hmm. Okay. And then we have 2 identical substituents. How do we indicate that in a structure?
1,2-methoxy.
1, 2, oops. But we also need a prefix,
Dimethoxy.
dimethoxy, right? Okay, cool. So ether naming, not too bad, right? Usually I'll say provide the IUPAC name of the compound below. If I say provide the common name, you're welcome to use the common naming scheme. Usually when I ask a naming question, I'm very specific so that you know whether common is okay. Sometimes I'll say, provide the IUPAC name, common alkyl group names, or like common alkyl prefixes fine, or something like that. So then you could use things like tert-butyl if it's a substituent or something like that. But as always, if you're doing a naming question and you don't know what I'm asking for, you can always send me a chat in the Zoom. Okay. It's not giving me the advanced button at the bottom. That's confusing. I want to advance. Okay, I'm gonna have to connect my keyboard back. Okay, there we go. So we haven't done a nomenclature of cyclic ethers yet. There's a couple different ways to do this as well. The IUPAC way is to say oxacyclopropane. Whoops, no. Seems to have permanently stolen the advanced button from the bottom. Okay, so then for a 5-carbon one, oxacyclopentane. And when you have 2 oxygens within the ring, 1,4-dioxacyclohexane. The common way of naming is actually for this type of functional group, which is called an epoxide. We're going to get to that at the end of the chapter. The common way is to name the alkene it was made from using the common naming, and then write oxide. So this is often called ethylene oxide. The next compound over has a common name, tetrahydrofuran, which you see all the time as THF. It's a common reagent that we've used. It's usually a solvent, or it's complexed with borane, things like that. And then the other one has a common name, 1,4-dioxane. So usually on exams, the reason you need to know these common names is because I might give you like a synthesis problem or a reaction where I give you it in words, and I might say ethylene oxide. Sometimes I throw in kind of freebie questions where I just draw a structure and I say, what is the name of this compound? In which case I would accept any of these. So knowing those common names can make your life a little easier for that. So definitely memorize these 3 common names. You are responsible for those. 1,4-dioxane, tetrahydrofuran, and ethylene oxide. Okay, physical properties of alcohols and ethers. I feel like we've maybe discussed this a little bit before when we were talking about solvents and such. But alcohols tend to have a higher boiling point for the molecular weight. So what that means is, in the example down below, all of these compounds have roughly the same molecular weight, even though they have slightly different numbers of carbons. These two have 4. These are actually isomers of each other, and this one has 5 carbons. Notice the boiling point for the alcohol, though, is 117.7 versus the alkane at 36 and the ether at 34. Alcohols are going to have lots of hydrogen bonding with themselves and also any other polar compound that comes into the solution. So lots of hydrogen bonding, which is what's affecting that boiling point. Small alcohols tend to be soluble or miscible in water because they tend to be liquids. So you would use the term miscible. And they are polar protic. Ethers are going to have very similar boiling points to alkanes of the same molecular weight. The reason being, if you have a solution, if you have a container of just diethyl ether, it has nothing to hydrogen bond with, so it's really just operating off of London dispersion forces the same way the alkane would be. It is polar, so there's a little bit more of a dipole effect there, but notice that does not seem to increase the boiling point. It's actually lower than that of the alkane. It can hydrogen bond with it cannot hydrogen bond with itself, but it can with polar protic molecules. So if you mix these two together, the ether would be able to create a hydrogen bond with the hydrogen from the alcohol. Small ethers are also miscible in water, and they are polar aprotic. They do not have a proton on them that can participate in hydrogen bonding. So that's really all I want you to know about the properties of alcohols and ethers. Okay, the synthesis of alcohols from alkenes. Please note this is a short review, essentially, from, what was this, chapter 8. So we've already seen these reactions before. What would be the product of reaction number 1? So we have we have propene, we're reacting it with water and acid.
Wouldn't the OH group be on the, trying to think, most substituted?
Yeah, that's exactly right. So this is an acid catalyzed hydration. You're going to end up with the most substituted alcohol. This is your Markovnikov addition. Okay, the next one is oxymercuration demercuration. Do you remember what product is formed from this one?
On the least substituted, so you get the anti-Markovnikov addition.
So I think you're thinking of the hydroboration oxidation. So number 3 would actually give us the less substituted product. This is our anti-Markovnikov. Whoops, sorry. What is oxymercuration demercuration, though? It's not anti-Markovnikov. It is Markovnikov, but it has kind of a special rule. So we're going to end up with the most substituted. Does anybody remember what is special about oxymercuration demercuration?
It doesn't have a intermediate step.
Right, it doesn't go through a carbocation, so there is no rearrangement possible. In this example, that doesn't really matter. There was no possibility for rearrangement anyway. But if there had been a possibility for rearrangement, this compound would not go through that if it was using oxymercuration demercuration. So these are your 3 alcohol syntheses from alkenes. And again, if you need some extra notes on this, please revisit chapter 8. which I think as a whole, as a class, I kind of really want you to go back over chapter 8. That seems to be kind of a weak spot for us. Okay, there are essentially 3 things that you can do with alcohols. This third one is very broad and covers a lot of reactions. The first 2 we're going to put on one slide. So alcohols can act as bases. You can take an alcohol, react it with an acid, that'll protonate it, and you end up with the conjugate base of your acid. We've also seen that protonating an OH group can turn it into a decent leaving group. So this kind of accomplishes 2 things at once. Alcohols can also act as acids. They can be proton donors. So if you react it with a base, or in this case just water, you could deprotonate it. Notice this equilibrium is heavily favoring our reactants. We'd have to put in a fairly strong base to deprotonate the alcohol. So this is kind of a chapter 3 revisitation here. Are there any questions about this page? Okay, this is where we're going to learn some kind of new stuff. This first one is just an SN1 reaction. This is not new to us. If you take an alcohol and react it with hydrochloric acid, you can displace the alcohol with the chlorine. This is an SN1 reaction. Do you remember how this reaction goes? What is the first step?
Doesn't the H on HCl attack the OH to make it H2O?
The outcome is correct, yes, but I just want to correct your wording real fast. It's actually the oxygen that will pick up the proton.
Okay, my bad. I switched that around.
No, that's okay. It's my job to be overly picky and correct you. So this would give us this, which I believe you mentioned could leave then. So this would be a good leaving group. That gives us an intermediate. And hey, we have chloride from our first step. All right, that gets us to our product. So this is just an SN1 reaction with an alcohol and acid. Can I erase that? Because the next reaction is definitely in that space.
Yeah, you're good.
Okay, similarly, you can do this with a primary alcohol. Notice the difference in conditions. This is at 25 degrees. This one is at reflux. Also remember, this is a primary alcohol. This is not going to happen through SN1. You're still going to protonate the alcohol, but then bromide is going to attack and kick it out once you have protonated it. So this would go through an SN2 mechanism. So the top one is SN1, the bottom one is SN2. You are not going to do an SN1 reaction on a primary carbon. Okay, this next one is new to us. I'm not gonna make you worry about the mechanism for this. If you're curious about the mechanism, I believe, no, I didn't draw it out in my notes, but I know Top Hat had it drawn out on a slide, which I can share with you guys if you feel like you wanna look at it. But ultimately, if you have a hydroxyl group and you react it with phosphorus tribromide, PBr3, you're going to end up with an alkyl halide. It's just a 1-for-1 displacement.
Does that say 4N on the bottom or 4H?
4H, sorry, 4 hours. So PBr3 cold temperatures, you're going to get your alkyl bromide and a side product. The stereochemistry for this reaction is retained. So if you did have a chiral alcohol indicated, I believe you would still end up with that chirality.
And you were saying that that's just one step, like there's no intermediate, it just goes straight to.
Yeah, there is a mechanism, but I'm not going to make you worry about it. So as far as you guys are concerned, this is a memorization one. So any alcohol, react it with PBr3, you will end up with an alkyl halide with just a direct displacement, no worries about carbocation rearrangements or anything like that. This next one is a very similar idea. You have an alcohol, SOCl2, which is called thionyl chloride. In the presence of pyridine, which will act as a base. Pyridine structure is an aromatic amine. So this is pyridine. You will end up with exchanging the alcohol for chlorine, and the stereochemistry will be retained. So this is another freebie to memorize. Alcohol plus SOCl2, thionyl chloride, and pyridine gives you alkyl chloride. Okay, so we've seen the reactions of alcohols with acid halides. This is not new. We literally just looked at this on the previous slide. But there are a couple of things to note. The order of reactivity is dependent on the degree of substitution of the alcohol. So a more substituted alcohol is going to react more easily. Also, as far as terms of the halogen acid, hydriodic acid is going to be more reactive than HBr, which is more than HCl, which is more than HF. This is based on the acidity. And the protonation of the alcohol is the first step. Tertiary and secondary are more likely to go through an SN1 mechanism. Primary has to go through SN2. So remember also that these have different stereochemical implications. With SN1, you end up with a racemate, a mixture. And for SN2, you end up with inversion. There's another way to accomplish this, which the reagents look very different, but it's actually the exact same thing. So you can take an alcohol, react it with a sodium halide in the presence of a strong acid such as sulfuric acid, and get the exact same thing. So what's happening is the alcohol gets protonated by the acid, just like you would in the other mechanism, and then you have your halide floating around. So it's the exact same mechanism, but where you get your proton from is different, that's all. So this is one of those reactions where anytime I give this on a quiz or a test, it's usually like a 50-50 hit. Like if I give something like this, most people get it correct, this top one. But if I give you guys this, about half of the students will get it wrong. And I really think the reason is that you guys tend to look at these reactions and say, well, I've never seen that before, so I cannot possibly answer that question. At this point, that is not how you should be thinking about this. There are some reactions that you can memorize, and I try to point that out to you. So this, memorize. This, memorize. That never, ever changes. But if you understand what is happening in this reaction here, you can do this bottom one even if you've never seen those conditions before. If you have an alcohol in the presence of a strong acid, there's only one possible thing that can happen. That strong acid is going to protonate that alcohol. So anytime that you're looking at a reaction and you do not know what to do, instead of saying, I don't know that reaction, I'm screwed, and skipping that question or just making a random guess, ask yourself what you do know about those conditions, because you guys do know a lot of information. I know that this has come at you really quickly, but that's another reason why memorizing is not the best method for OCHEM. You've probably also noticed as you're doing your homework that there are so many problems that can be created around even the simplest of reactions, right? I can give you literally any organic alcohol. I can give you so many things, and then there are so many different reagents I could react it with. If you are focusing on memorization, you're not going to get very far. You can memorize these reactions, but you also have to understand how they work. So you see an alcohol, you see a strong acid, you protonate the alcohol. And then you look at your other reagent and you say, okay, well, I know sodium never appears in my products, right? I'm not going to use that sodium. But I've seen what happens with an alkyl halide, or sorry, with a halide and a protonated alcohol. So if you look at it that way, you can solve pretty much any problem. If you don't look at the alcohol and the acid and say, I'm going to protonate that alcohol, start at the acid and say, what is the goal of the acid? It's a proton donor. Do I have anything in my reaction mixture that can accept a proton? Oh, look, I have this thing that has a bunch of electrons on it. Or, oh, look, I have this halogen that could pick up a proton, I guess. That would be wrong. But if you came up with HX, you would then have an alcohol and HX, and you do know that reaction, right? So there are a lot of ways to get to something that you do recognize, but I don't want to hear you guys looking at a problem and going, well, I've never seen that before. This is unfair. I cannot do this. That's you not believing in yourself. I tend to believe in my students like to an extreme level. And then I hear from my students that they have very different feelings about their capabilities. You can do this. You just have to be willing to do it. So that being said, this reaction, the next one, is also a very similar idea. With a primary or secondary alcohol, the zinc 2 chloride is going to act as a Lewis acid. I'm not going to make you worry about the mechanism of this. It's just like the zinc is coordinating with the alcohol to make it easier for it to leave, but it's going to give you the same effect. So this one is one that you can memorize because it's always going to be sodium chloride and zinc chloride with an alcohol to give you an alkyl halide. This top one, I could give you any alcohol, any halogen salt. It could be potassium, it could be sodium, it could be chloride, bromide, iodide, fluoride, and any strong acid. So that one you cannot really memorize. But this one you can, the bottom one you can. Okay, this next slide, I said that you could turn alcohols into better leaving groups. So far, the only way that we've seen that is by protonation. There are also these kind of more complicated leaving groups. Notice they all have a very similar feature. They have the sulfonate. And if you look at these, the top portion is describing the substituent. So this is the tosyl group, also known as the toluene sulfonyl group. That's the long-term name, but tosyl is fine. The shorthand is TS. This next one is the mesyl group. This is also shorthanded as MESO2 or MS. The next one is the trifle group. You can shorthand it as CF3SO2 or just TF. And all of these can be combined with alcohols. Typically you have like tosyl chloride, mesyl chloride, trifle chloride, and you react them with an alcohol to create an alkyl tosylate, TSOR, an alkyl mesylate, MSOR, or alkyl triflate, TFOR. And what this does is this carbon that's attached to the alcohol can now be attacked by a nucleophile because this is a good leaving group. So you can kick out the oxygen that was part of the alcohol as long as it's attached to something else to stabilize it. So for example, if you react ethanol with mesyl chloride in the presence of pyridine, pyridine is acting as a base, you'll get ethyl methane sulfonate or ethyl mesylate. Or you can react with tosyl chloride and ethanol and pyridine, and you'll get ethyl p-toluene sulfonate or ethyl tosylate. The reason that you would do this is that you can now attack this carbon with a nucleophile and kick out a decent leaving group, which we're going to see on the next slide. Oops, oh, poor animation. Oh, I thought I had it right. Dang it. Okay. So you create your alkyl sulfonate. That the term sulfonate is going to include mesyl, tosyl, and trifle. You can then attack it with a nucleophile and kick it out through an SN2 mechanism so that you are able to do an SN2 reaction on an alcohol, essentially. Does this idea make sense? It's the same idea as protonating an alcohol to make it a good leaving group. This is just a much more complicated leaving group. So do you think that I want you to memorize these structures?
Yeah.
Yes. Notice you just have to memorize these, right? It's the same thing below, just with the alcohol attached. So flashcard, right? And then if you fail to memorize them, that just means like you won't know tosyl, mesyl, trifle. You may not recognize the shorthands when you need them. But if the structure is drawn out and you see this, you need to recognize that as trying to create a better leaving group. You're not going to see that for any other reason in this course. So we have our better leaving group. We can do an SN2 reaction. I did write out the mechanism of how the alcohol reacts with the sulfonate. So I did this with mesylate because it's the easiest one. Easiest just meaning less to draw out here. So the alcohol is going to attack the sulfur, and you push the electrons up onto the oxygen. And then the oxygen's electrons come back down and kick out chlorine to reform the double bond. This is not really chemistry that we've seen yet. It kind of mirrors chemistry of a carbonyl, which is not something we've done. In OChem 2, we do a lot of carbonyl chemistry. I'm not going to test you over this mechanism, by the way. I'm just showing you how it works so that you understand. So the electrons come down, you kick out the chlorine. Now you have this reformed, and you have it attached to the oxygen of the alcohol. Notice it's still protonated, so that's why you have to have pyridine in this reaction. Pyridine is a pretty decent base, and especially when you have a proton as acidic as this one, you can deprotonate it pretty easily. And that gives you your alkyl mesylate plus pyridinium as your conjugate acid, but that's not really important. So that's how the alcohol is reacting with like mesyl chloride. Okay, so we have a top hat question. Make sure you are logged into Top Hat. This is not the question. Also, it's important to note that these reactions with sulfonates have retention of stereochemistry. Okay, it's not clicking. I have a bad feeling that it's presenting the wrong question. Hold on.
Don't you just love Top Hat?
I think it's more my, yeah, this is the wrong question. I think it's my internet. It just cannot handle Zoom and Top Hat. Sorry, do not answer this question. You've answered it before. Okay. Why are you being this way?
Because we're watching.
Yep. I even went through the trouble of picking out these questions so that you guys could get some points.
We're giving the internet performance anxiety.
Seriously. I don't understand why it doesn't get that we're a team. Okay, so let's take attendance real fast.
There's no such thing as real fast with Top Hat.
I meant you guys be quick on your side.
Thanks again for like going through the test and kind of giving us a curve. I appreciate that.
Oh, no problem. There weren't as many questions to regrade as I thought there were. So then I kind of actually organized all the questions based on your performance. And then I went through and read each question and tried to decide if you guys deserved to suffer that question or not. So the ones that you guys missed that I thought were easy, I didn't give you points back for that. For ones that were a little more challenging, I kind of took a tally and basically gave you a curve worth the number of questions that I thought was a little too difficult. Maybe not too difficult, but were difficult over this exam period, I guess.
Yeah, you seriously helped me out. So
Yeah, that's actually, it was a curve of 16 points, which is actually pretty normal for OCHEM. The grade, like the average had been like a 55 or something like that, or 54 once I finished adding in some points back from regrading some questions. And that really is a pretty normal curve. I usually don't curve my exams as much. I usually make students do test corrections, but that's not really doable with an online test or over the summer. So, okay, I'm gonna minimize this.
I have a question. Did we ever decide on the moving to 15% homework and then 15% participation in class?
No, that's a good question. Nobody ever emailed me as to why they didn't want to do that. It's not too late though. We can still decide on that. So if everybody would just please think about it, we can revisit this tomorrow. Basically, everybody has pretty high homework grades. I am probably going to go through and drop your lowest homework grade. I didn't want to announce that because I'm worried that somebody's gonna be like, well, I don't have time to do chapter 11, so I'm just not going to. Please don't take that approach. You need to do your homework in order to be ready for your exam. But I'll probably drop a low assignment. And then I was considering giving extra credit for anybody who actually does the in-text questions for the chapters I did not assign. But I haven't decided on whether I want to do that or not.
For the in-text problems, whenever I leave the reading, they reset.
Yeah, that's because they're set for review right now. So I'd have to make them for a grade in order for that to happen, I guess.
Oh, okay.
Would you guys rather I turn it on for like marked as 4 grades that you can keep your progress? Because I can do
I
that.
have
It won't affect anybody.
the one thing I really like
Yes.
about those reviews though is that when you get it wrong, it'll show you what's correct. I don't know, like I feel like you can go back and sort of go like, oh, and track it back a little bit better, but the credit would be nice.
Okay. I'll think about it and let you guys know by tomorrow. So remember, this is going to have retention of stereochemistry in that first step. So your mesylate will have the same stereochemistry as the alcohol. And then you need to decide if the second step is going to have an effect on your stereochemistry. Okay, about 30 more seconds to wrap up. All done. Yeah, today there really is no such thing as real fast on Top Hat. Yeah, it's doing the thing where I click a button and then it acknowledges it a full 7 seconds later. Okay, so we have very, very mixed results. Do you guys still see a stop answering button in the middle of the screen?
Yeah.
Yes.
Yep.
It'd be cool if that would go away. There it goes. Okay. So let's discuss this. What is happening in the first step? We have methyl chloride and pyridine. What are we making?
You're basically just substituting the OH group with the methyl ox, or that whole thing.
Right. So we're making an alkyl mesylate. So after step 1, remember this has retention of stereochemistry. You should have OMS. Okay, and then step 2, what is happening? What is this?
The leaving group.
The opposite of a leaving group is what?
Nucleophile.
Nucleophile, right? Yeah. So we have our leaving group here. That sulfur with a negative charge is a nucleophile. Wow, even the annotation is chunky today, and this is not the Top Hat one. This is the Zoom one. It must be my internet. Okay, so this is going to do an SN2 reaction. We kick out our mesylate. What is going to be, so which ones should we go ahead and eliminate? Which products are not even including our nucleophile?
1 and 3.
Right, so these are no-goes. That is the product after step 1. But in step 2, we are doing a substitution. And what is the stereochemistry going to be? Are we going to have the same retention, or are we going to have an inversion?
Inversion.
Right, this is an SN2 reaction, so you should end up with an inversion. So number 2 should be the correct answer.
Nice.
Whoops. By annotations, okay. And yay, that's the one that got the most votes. Oh, come on. Let's go back to PowerPoint. Okay, so I can bring up the forward arrow, but I cannot use it. Come on. Okay. That's the wrong way, computer. So maybe the technology is just against me today. This is going poorly. Okay. So we're going to discuss some methods to synthesize ethers. Most of them are things you've actually seen before. So this first one is intermolecular dehydration of alcohols. That sounds really complex, but it's really not. This is essentially an SN1 reaction where one alcohol is a leaving group and the other one is a nucleophile. So for example, if you take ethanol and you heat it up in sulfuric acid at 180 degrees, you would just get ethene. If you take that same alcohol, heat it up at a slightly lower temperature, you could end up with diethyl ether. This is not the type of question I would give you guys. This is ridiculous to have you memorize like 180 versus 140. But I want to go through the mechanism of this. So you're going to use 2 molecules of ethanol. And one of them is going to get protonated because you're an acid. That turns it into a good leaving group. So then the other equivalent of the alcohol can come and attack the carbon and kick out your water. And then you have to deprotonate your water. So if we're color coding here, so then you use the water to deprotonate because you're still going to have the hydrogen from the alcohol attached. And that leaves you with your ether. Now, this is problematic for a lot of reasons. One of them being that you're definitely going to have a mix of products. If you do this with 2 primary alcohols, it's essentially a crappy reaction. It's not going to give you very much of what you're looking for. And if you're using 2 different alcohols, you're going to end up with a whole mix of problems. So if you have ROH and R prime OH, you're going to end up with ROR, R prime OR, R prime OR, R prime OR prime. Try saying, just try reading that out loud. That was challenging. Okay. Plus water. So One of the things that you've probably noticed in OCHEM so far is that if you're going to end up with a huge mix of products, that's probably just not a good reaction, right? That's not ideal. Usually if you're trying to do a reaction, it's not just, oh, let's mix these two things together and see what happens. Usually you're doing a reaction because you have a goal in mind. You want a specific product. So if you're going to end up with, you know, a 33, 33, 33 blend, which I don't know if that's what would happen, that's not going to be overly useful. So there is an exception, and by exception I mean a way to manipulate this. If you need one side of that ether to be a T-butyl group or some other heavily substituted group, then you can mix a primary alcohol with that and you will get one product. The reason being that when you protonate that very highly substituted alcohol and the leaving group leaves, you're going to end up with one very good electrophile. And then the primary alcohol can attack that and you'll end up with one product. If this carbocation can form, you're not going to create a carbocation from a primary alcohol or use this as a nucleophile on a protonated primary alcohol. That's just not going to happen. Not when this can form. So that's one way that you can manipulate this to get it to work for you. The other issue still though is that you are still going to get elimination because this is an SN1 reaction. Remember that SN1 and E1 go hand in hand. So even though you can manipulate this reaction to work, if that's if your goal includes a highly substituted carbon, you're still going to end up with elimination as well. So that's kind of the downside to this type of reaction. Are there any questions about this? Okay. So there is a slightly better option called the Williamson ether synthesis. And I say slightly better, it's significantly better, to be honest. This is the best route to asymmetric ethers. It goes through an SN2 reaction, which means you don't have to worry about carbocation intermediates. And as long as you've picked everything correctly, you might not have to worry about elimination either. So you have an alkoxide and an alkyl halide typically. And the alkoxide is going to attack the alkyl halide. The halide is your leaving group, and you end up with an asymmetric ether. The leaving group tends to be bromine or iodine, but you can also do this with a tosylate, a mesylate, or a triflate. And that's a really common like multi-layer problem. I have you react an alcohol with tosylate or tosyl chloride or mesyl chloride or triple chloride, and then I give you an alkoxide to react with. This works best with primary or methyl for the alcohol or the alkyl halide. Both of those are going to be better if they're less substituted. Typically, whatever the longer side of the ether is tends to be the alkyl halide. And if you're going to have a methyl side, you typically want that as your alkoxide because that makes your nucleophile as small as possible. But either way, it's going to work because a methyl group can only do SN2 reactions. So if you have a methyl halide being attacked by like ethoxide, you don't have to worry about elimination. So there are benefits to either way. I have, in fact, given a question before where I asked which one was better to do something like this or this. And the bottom one can actually be a little better because, sorry, I should have just written CH3. That would have been less obnoxious. Okay. The bottom one is actually a little better because there's no chance of elimination on a methyl group. So you can only create one product. this one is definitely going to work. You're going to mostly get your ether, but you also have the possibility of elimination. But it'll be very slight. That has been a test question in the past. And I still really like that question, even though I just gave you the answer. If you had a tertiary alkyl halide, you would get exclusively elimination. So you can't do this with a tertiary alkyl halide. Just remember, you can't do an SN2 reaction on a tertiary alkyl halide. Okay, we have 6 minutes left. That gives us plenty of time to go through phenols in the Williamson ether synthesis and then do a practice problem. So if you have a phenol, such as the one on the top left here, you can react it with sodium hydroxide. Remember, the pKa of a phenol is around 10. So you can actually deprotonate it with sodium hydroxide because your conjugate acid would be water, which has a pKa of about 15.9. So you're going to favor this side with the phenoxide. And that creates a good nucleophile, which can then react with an alkyl triflate to give you an ether. So phenols are really nice in the Williamson ether synthesis because they are easily deprotonated just due to their higher acidity than alcohols. But that being said, here is a practice problem using an alcohol, and I gave you a base that we have seen before, but you may not remember. This is sodium hydride. So I just want to give you, I'll give you 2 minutes and I'll go ahead and put you in breakout rooms just so you guys can bounce ideas off each other and maybe get through it a little faster. So go ahead and go to your breakout room. I'm going to give you about a minute and then I'm going to close them, but you can still stay in there if you need that extra minute.
The H, the H and the NaH is negative? Is that what you're saying?
Mm-hmm. Yes, this is sodium plus and hydride, which is a base. So what's happening in the first step?
Right off the bat, it's going to, or I guess the OH would attack it.
No, actually the other way, because it's acting as a base. So the hydride is
There's an interaction going on between the OH and that, basically, yeah.
Yeah. So the hydride is going to pull the hydrogen off of the alcohol. So after step 1, we have an alkoxide. And then we are adding in an alkyl halide, a primary alkyl halide. What's going to happen then?
Does the sodium interact with the second product, the bromine, and take it off the ring?
Not the sodium. We don't want to use the sodium. But we just made this for what purpose?
Would that attack the bromine?
That would attack the carbon next to the bromine and kick it out.
Okay.
This is literally what's happening right here, right? We made an alkoxide and then we attacked something that had a leaving group. So then you end up with an ether. Whoa, sorry, I was thinking about oxygen. So I drew a circle. So that's the Williamson ether synthesis. Okay, that seems to have thrown us for a bit of a loop. And yet we didn't have questions on the previous slide when this was introduced.
I think that the hydride threw me off.
Okay, even though I said out loud that it was a base, I thought I was being helpful.
No, when you said that it made sense, but like on my own, I was like, hold on, this is backward.
Yeah, that happens. Okay, so we are out of time today. So we're gonna pick up here next time. We don't have that much left of chapter 11. We do have several top hat questions to go through, but I was looking through my binder here. We only have 6 pages of chapter 11, and some of them are going to be very, very fast. So we are definitely going to finish chapter 11 after the quiz on Friday. If we don't, it'll be because Top Hat is slow. Yeah, so please work on your homework. I will open up chapter 11 homework for you. The quiz is going to focus more on chapters 9 and 10. But I'm also intending on putting a little alcohol nomenclature on there. But expect to see 9 and 10 on the quiz. All right, I'll see you guys tomorrow.
Thank you.
Did all of the homeworks get moved to, like the due date get moved to the 4th?
Yes. Mm-hmm.
Okay.
That's our new exam.
So there's nothing due the, okay, so there's nothing due the 31st now?
No, I'm gonna leave the homework open through the up to the exam so that you have something to practice with.
Okay, perfect. Thank you.
Mm-hmm.